Continuing with our circle unit, we're going to talk about tangents today. The stuff that we're discussing applies to both circles and spheres. The math does not change. It's a little hard to show the sphere idea, but you'll see in a little bit what it looks like as a circle. The first thing that's going to be a little strange is we've talked about tangents when we're talking about trig with right triangles, that relationship between the opposite and the adjacent sides. But we have a different definition of what a tangent is when we're talking about these 2D and 3D shapes with circles and spheres. So a tangent is actually a line that hits a circle once. And sometimes it might look like it's hitting it more than once, but if you were to zoom in, it's only hitting it once. And there's some specific things that happen, some nice things that happen that allows us to find some things that are missing. So the first theorem to take a peek at is if that line is perpendicular to the radius, then it's a tangent. And the other way around, if you have a tangent to a circle or a sphere, then it is perpendicular or 90 degrees with the radius of either of those objects, because spheres also have radii. This is what it looks like visually. If we're talking about the radius and the tangent, they are 90 degrees with each other. So that does allow us to create our right triangle situations and find some stuff that's missing. So our first example, I just find this one kind of interesting. The question is, if we were sitting at the top of this roller coaster, how far could we see? Now, there's some other things in science about refraction and things like that that would affect how far you could actually see. So we're saying in a perfect mathematical world, how far could you see, to the horizon? So we're going to start this first example with being 456 feet above ground, but we also need to know the radius of Earth. Now, Earth is not a perfect sphere, so we're just going to use a rough estimate for what the radius is, which is just shy of 4,000 miles. So to do this problem, first thing I'm going to do is we need to have the same units. So I'm going to convert the height of that roller coaster into miles. So we're talking everything in miles. You could do the same thing with feet, but 3,960 miles is a lot of feet. So that'd be a really big number. So in the picture, if you notice this right here, and it's an exaggeration just because it's so tiny if you were to actually draw Earth, but let's say this is our roller coaster and we're sitting at the top of the roller coaster. So we're less than 1/10 of a mile off the ground. If we continue that line straight through to the center of Earth, that would actually give us our hypotenuse in this right triangle. So it's the radius plus the height are going to be our hypotenuse. And then one of our other sides of our right triangle is just straight up the radius. So using the Pythagorean theorem, we have a squared plus b squared equals c squared. I'm calling how far can we see x. You could call it a or b, you can call it whatever you want, but it's from the top of this little green roller coaster line to right here, where the Earth starts to curve again and you couldn't see any further past that. So you could type those in, and with our calculators now, you could actually do this, again, an all-in-one step when we talked about our Pythagorean theorem. So that's the way I'm going to show it. You would square everything. You could then subtract the radius squared from the left side, also from the right side, and then we would finish with the square root to just get x. So after all that calculating, in a perfect world, no obstruction and no crazy science stuff going on with the sky and light and all that stuff, you could see just over 26 miles. Our last example, same situation, but we're going to go up a little bit higher. So we're going to look at the top of the highest building in the world, which is now 2,717 feet up. So it's a little bit higher than that roller coaster. We're still going to use the radius of Earth, that same number, and so the process is going to be the same. So if you felt good with that first example, you don't really need to look at the second one, but I just find this one kind of interesting. Not a huge fan of heights, so this is crazy. I think that right picture almost looks fake, but it's not. So same process. We're going to convert the height of the building into miles by dividing by how many feet are in a mile, 5,280. And so that building is actually a little bit more than half a mile up in the air. So we can then go with our Pythagorean theorem. We're going to square everything. And again, that hypotenuse is the radius plus the building. We square it. We subtract the stuff off from that left side. We do the square root. And at the top of this building, mathematically, you could almost see 64 miles. So visualizing that, I think that's kind of fun. If you were to go to where this is located, and I put the building at the center, that's how much you could see. Now that does, unless you're a huge geography person, you might not know where we are. You might not know, oh, is that big? So let's give you the reference for Belle Plaine. If they built that building in Belle Plaine, how much of Iowa could you see? You could start to see the outskirts of Des Moines. It's absolutely nuts.